Hello everyone, we're going to be doing double integrals again, but over a general region. And then tomorrow we're doing double integrals in polar coordinates. And then maybe the day after, because it's going to be Monday, we'll just get started on triple integrals. Okay? It's pretty exciting. So, yeah, yesterday we looked at double integrals with the rectangular bounds. Now we're going to look at them with general bounds, and what that just means is the bounds could be described by different equations. So like before we just had like rectangles or squares, right? But now like they could be like circles, or like maybe not circles, but later on, and then you could have parabolas, sideways parabolas, I don't know, lines as your regions, stuff like that. But yeah, not just rectangles. So how would you describe these? Well, you describe them with equations. So you'll have different equations in your integral bounds. It's crazy. Yeah, so you're going to have line formulas and parabolas in your equations rather than just constants. Another thing to note is last video with rectangular bounds, we saw that you could, so if you had something that was from like 0 to 3, and then 2 to 5, and then I don't know, some function of x comma y dy dx, you could just switch this, and so what that means is this is equal to this. Okay, but with these general regions, you can't just do that. You're gonna have to take some extra steps, and you'll see why. Another thing to note is, last video we really just looked at double integrals doing volumes, but they can also do areas. Okay, so it's kind of a weird, and I found myself stumbling over this quite a bit when I was learning how no one really explained it to me, but double integrals can do areas in any kind of area in 2D space, but they could also do volumes in 3D space. Okay, so double integrals do areas between curves in R2, but they do volume from z equals 0 to the surface in R3. And to find the volume between surfaces, you'd need a triple integral. But that's for later. This is what we have to know so far for double integrals. Okay, what else? Oh yeah, so the reason that they could do areas between curves is because, so you remember maybe in like Calc 1, in Calc 1, if you had something like, okay, wait, why am I writing with a pencil? Sorry guys. It's been a long day. Okay, yeah, so imagine you're in Calc 1 right now and you're learning about areas between curves. Your teacher is probably describing them like that. So if this is f of x, and this is g of x, okay, and you were sitting on this interval of a to b, and you wanted the area, okay, maybe g isn't drawn too well, so, and you wanted this area, how would you find it? So you know that you'd do from a to b of top curve f of x minus g of x, and the reason why is because if you just do the integral from a to b of f of x, you're going to get all the area under f of x from from y equals 0 until f of x. Okay, so this is the area that you get. I'll just draw it out. So suppose this is f of x, this is a, this is b. Doing that integral is going to give you all of this. Doing the one for g of x, this is a, this is b. Doing that integral is going to give you this. Okay, so subtracting these two areas, right, it's going to give you this region up here. which is what you want, right? Because we want the area between them. Okay. So the double integrals, you could use a double integral for this. It's kind of overkill, but you can. You could just say it's the double integral from a to b, and you go from g of x to f of x. And then this is going to be in dy dx. Okay? Those are equivalent. And it makes sense, because whenever you evaluate an integral's bounds, right, so if you got a 1 in here, then you integrate them, you're going to get, so if you do this innermost integral, if you evaluate the 1, you're going to get a y, and it's going from g of x to f of x. And then this equals f of x minus g of x. So it's the same as that, right? And yeah, it's the same thing. Okay, so that's how you get areas with between curves with double integrals. Another thing you want, oh yeah, maybe you could even observe it here. I said earlier you can't switch the integrals, the order of integrals, like this, if the bounds aren't constant. So here we see that our bounds aren't constant. Well, I mean the a and b are constants, but f of x and g of x are not constants. So you cannot say that, I'll just write it down here. You cannot say that this integral, oops, that is an f. You cannot say that this integral right here that we wrote earlier is equal to this guy. And honestly, it doesn't make much sense, because you'll see that here, we'll look at it in a second. Those are not equal. Yeah, and you can see part of the reason is because if you were to evaluate this, okay, so you have this, you evaluate this, and then you get b minus a, and now you're integrating b minus a with respect to dy, and then whatever you get out of that, you're going to put functions of x in there. So if you computed all that, you would get a function. You would get some kind of weird function that doesn't really mean anything, when in the whole time you're searching for a number that would quantify area. So yeah. Okay, so that's why you can't just switch them. What you would have to do actually is you'd find other constants, call them c and d. If you wanted to switch the order, that's what I'm talking about. You'd find other constants, c and d, and now you're going to describe these as g of y and f of y, okay? And then, yeah. And that also makes a lot of sense, because now you're going to get functions of y out of this integral, and then you're going to integrate these functions of y with respect to y, and that makes sense, you know? It makes a lot of sense. Okay, so we can get started on some examples. I have quite a few examples to go through with you guys today. So yeah. So, okay, this first one, we have find the area between y equals x. So the area bound by y equals x and y equals x squared. So it is, sure, it's easier to do this the Calc 1 way and just do one integral, but just so we really know what we're working with, we're going to do it with a double integral, okay? So if you drew this out, y equals x, you know, just a straight line. Okay, that's y equals x. And then the y equals x squared, that's like a parabola. Okay, why am I not doing full lines? Okay, so we want this region bound between them. Okay, all right, so you can start with saying, okay, well, these points that they intersect are pretty important. So where do they intersect? So they intersect at x equals 0, y equals 0, and at x equals 1, y equals 1, right? This is pretty obvious, because if you set these y's equal to each other, you're going to have x equals x squared. That only happens when it's 0. Then you can cancel it out, cancel an x out, and you get 1 equals x. So 2 solutions, right? So yeah. So we can say that our integral, we have 2 paths here. We could go from, we have 2 orders we could do, right? We have dx, dy, or we could do dy, dx, okay? Let's just choose one. We'll do dx, dy. We can do both if we really want to, but that's for later examples. Or actually, let's do dy, dx. Let's do dy, dx, because that'll be easier. Dy, dx. Okay, so this is gonna be like our blueprint right here. So we have this, and then we're finding area, so we don't have a z to integrate. And then we chose the order of dy, dx, right? All right, first rule we said is the constants are always in the outermost integral. Okay, so if we split up our integrals here, our outermost integral is dx, and we just have to ask the question, oh, where does the x stretch from? Well, x stretches from 0 till 1. Okay, so he's going from 0 to 1. All right, now what about y? Where's y stretching from? How I do this, I mean, maybe it's easy for you guys to see, but I remember when I was learning it, it was pretty difficult for me to see. How I do it is I say, all right, so we're going in the y direction. So I choose a parallel line that's going in a line that's parallel to the y-axis. So I choose this line right here. So we're coming in, and then, okay, we hit our first curve. That's y equals x squared. We hit the parabola underneath. So he's going to go in our bottom bound. All right, so we're going in, we're inside the region, and then, we hit the other one, and now we're coming out, okay? Oh yeah, this line has to go in the positive y direction, by the way. Okay, so we hit our first curve, we said that was x squared, right? And then we hit our second curve, that's x, okay. So y is going from x squared to x, right? Okay, cool. So this is we can evaluate this. Okay, so we're going from 0 to 1. There's a 1 in here that you can't see. Integrate the 1, you're going to get y, and y is stretching from x squared to x. If you evaluate that, you're going to get x minus x squared. All right, so we're done with our inner integral. Now we're doing this. This is just an easy power rule. So you're going to get half x squared minus 1/3 x cubed, and he's going from 0 to 1. So you have half minus 1/3 minus just 0. Okay, so this is 3 out of 6 minus 2/6. So that's just 1/6, right? So yeah, so this is the double integral setup, and then this is the Calc 1 approach integral you'd get. They're both literally the same thing. Okay. Now let's do a volume one, okay? We can do a volume one. Let's find the volume under z equals xy. And the region that it's bounded by is going to be y equals x and y equals x squared. So it's the region we just found. Okay. Now we're integrating an actual function this time. So and the region that we're doing is the same as before, so we can set it up the same way. So we take these guys and we'll do dy dx, and we're going from 0 to 1, from x squared to x again. And and we're going up till we're integrating xy, okay? All right. So we're integrating in y, so we can pull this guy out, okay? Plop him in here, because he's a constant. We're integrating in y, remember? So this guy is equal to 0 to 1 x times the integral of x squared to x of y dy dx. All right. You might remember before I said if you have if you have a function in here that could be written as a product of two things. So in this case, the xy could be written as x times y, the product of those two things. You can split the integrals and do them completely separately. Yes, that's true, but only for rectangular bounds. So this is not equal to, sorry about that, 0 to 1 x dx times x squared to x y dy. Yeah, you can't do that, and that makes sense. It's kind of similar to before. You could see that out of this integral, you're going to get a constant, and out of here, you're going to get a function of x, and that doesn't make sense. Okay, so you're going to have to keep it this way, right? So this is a not equal sign. Okay. All right, so rather, if we do our innermost integral, we're going to get, well, what is this? This is going to become half y squared. All right. Maybe I'll zoom in a little bit so you get the full page. Okay. And he's going to go from x squared to x. So you're going to have half x squared minus half y to the half x to the fourth dx. Okay. Okay, you could distribute this. By distribute I mean this x. You could distribute him. So 0 to 1, and then you're gonna have half x cubed minus half x to the fifth dx. It's another power rule. You could also whip out the half. And you're gonna have 0 to 1 x cubed minus x to the fifth. All right, so this is just half times 1/4 x to the fourth minus 1/6 x to the sixth from 0 to 1. Thankfully, that's not too bad. You're going to have half times 1/4 minus 1/5. Okay, so this is equal to 1/8 minus 1/10. So you're going to have okay, sure. You're going to have 10/80 minus 8/80, and that's just going to be 2/80. Which is 1/40. Okay. So I actually don't think I think I made a mistake somewhere here. So I'm gonna double check. Okay, I'm really stupid. This is this is supposed to be a 6. My bad. Okay, so you have 1/8 minus 1/12. Now you could turn that into 3 out of 24 minus 2 out of 24, and you get 1 out of 24, which is the right answer. Okay. I wrote a 5 there instead of a. Wait, and then I wrote a 5 here instead of a 6. Okay. But yeah, that's how you do that. And we were doing the same reach over the same area that we were doing last time. So we didn't really have to put much thought into making the integral. All right. Next problem. What is it? All right. This one is one where I want to emphasize swapping the, what do you call it? The God damn it. The bounds, the order, right? So we're going to do that in just a moment. Just find it. Yeah. Okay, so we're going to be finding the area between y equals negative x squared plus 3 and y equals x squared. Okay. So this is an area, so we're going to be drawing this in R2. So, okay, I'll just keep it. So if we draw our little plot over here, y equals x squared, that's pretty standard. It's just this parabola. And then y equals negative x squared plus 3. Say this is 3. Put a 3 on the y-axis. It's just an upside down parabola. Okay, and we want this area. Okay. Now, so we have two choices of orders. We have dy dx, right? And dx dy. Okay. Well, let's first, we'll do the easy one. We'll do dy dx. Okay? So we're going to have this set up. And then we're not integrating anything because we're finding for area. And we know that our outermost integral, which in this case is the dx integral, has to be constants. So we'll choose these. That's the range of x's we're going to be doing. So let's find those x values. So to do that, we're just going to set these equal to each other. So x squared equals negative x squared plus 3. That's 2x squared equals 3. X squared equals 3 halves. So then x equals plus or minus root 3 over 2. Okay? So this guy goes from negative root 3 over 2 to positive root 3 over 2. Sorry, this radical is supposed to get the whole thing. Okay? All right, now what about our y? Our y is going to be a function of x, okay? So we got to pick our favorite line. So, and this guy has to be parallel to the y-axis, pointing in the same direction as the positive y-axis. So this is the y-axis, this is the x-axis. So we're going to choose this guy right here. He's going to be going in that way. So he's traveling, boop, 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 boop. All right, he's hit him. He's hit our first curve. The bottom one, that's x squared. All right, now we're in the region we're going to be integrating for. And then we hit the topmost curve. He's negative x squared plus 3. All right, and then we're out. That's all we got to integrate. Okay? So this is our integral. That means if we partially evaluate him, we're going to get integral from negative root 3 over 2 to positive root 3 over 2. And then there's a 1 in here. You're going to get negative x squared plus 3 minus x squared dx. Integral, I'm going to call this a. So this is going to be minus a plus a. I don't feel like writing that all the time. Okay, so you're going to have minus 2x squared plus 3 dx. And then you're going to get negative 2/3 x cubed plus 3x from negative a to positive a. Plug those values in. That's so ugly. You're going to have negative 2/3 times, that's going to be 3 over 2 times root 3 over 2 plus 3 times root 3 over 2 minus, God, this is so ugly. Oh, I think actually stuff cancels though. Oh, well, this is gonna be negative. Plus, well, I guess it's gonna be minus now, 3 root 3 over 2. Okay, right, let's make sure we're consistent with the signs. If you cube this guy, you're gonna get a positive. If you cube this guy, you're gonna get a negative. So you're gonna have a minus plus a minus. Oh, damn it. Cancel. Shucks. Okay. Alright, so what cancels? This guy cancels, this guy cancels, this guy cancels, this guy cancels. Okay, I guess that's kind of nice. So you're gonna get negative root 3 over 2 plus 3 times root 3 over 2 minus positive root 3 over 2 minus 3 root 3 over 2. All right, so this guy's 2 root 3 over 2. And then this guy is negative 2 root 3 over 2, so you're going to add them like that. Right, because you get a negative 2 and then add the negative. Okay, so total we have this guy as our answer. Okay, let me double check that with my calculator, make sure I think it's right though. Yep, that's our answer. It's roughly 4.89897. Yeah, so that's the right answer. This guy right here. Oops. Okay, that's the easy route. Do we want to do the, okay, how about this? I'll only set up the hard route. I'm not gonna solve it because we're obviously gonna get the same answer. You might be inferring that the hard route is choosing this order. Why is that the hard route? Well, here's what's gonna happen. So this is our little blueprint, dx dy, right? We're not really integrating, we're just integrating 1. All right, our outermost integral, that guy has to be constants. I'll redraw the little picture we have. So this is x squared, and then this guy is negative x squared plus 3. We want this area, and then this is at y equals 3. All right, so we'll start with our outermost integral. That's going to be constants. So where does y stretch from? Y is going to stretch from this itty-bitty point right here, which is 0, right? Because our bottom curve is x squared, and he's going to hit 0. And he's going to go all the way up to 3, okay? So he's going from 0 to 3. All right, that looks better than plus or minus root 3 over 2. The real kicker, or why the fuck did I, okay. The bad part comes here when you're gonna do the dx. All right, so dx, where does x stretch from? Because right now what we have is if we're going from 0 to 3, we have this integral between these guys, which is pretty much infinite, I guess. Yeah. So what's happening now is we have to limit this space in the, what do you call it? In the x region. Yeah. So how do you do that? We want to limit it to this. So we're going to choose, similar to how we chose our favorite line of y that's parallel to the positive y-axis, we're going to choose our favorite line of x that's parallel to the positive x-axis. So we're going to choose this guy right here. He's going that way, right? Because that's where the positive axis goes. So where he's going to be going, he's moving, he's moving, he's moving. All right, he hits the curve. That's negative x squared plus 3. Okay, so he's hitting negative x squared plus 3. All right, and then he's moving in the region. Oh my god. Oh my god. He hit the same, the curve hit itself. Okay? The curve hit itself. So what do you do? What do you do? You can't integrate from negative x squared plus 3 to negative x squared plus 3. That doesn't make any sense. Right? So I wasn't pleased with the explanation I put in the back, but sorry, I just redrew everything. But so what you're gonna do is you're gonna split them right here, right at their intersection points. Okay, and keep in mind that when you're doing this dx integral, out of it you should get functions of y. Okay. So this guy, remember, he's x squared, and the top guy, right, that guy, is negative x squared plus 3. Okay? So you need to turn them into functions of y. So you have y equals x squared, y equals 3 minus x squared. So this guy is going to become x equals plus or minus root y. And then this guy is going to become x equals, what is that? Plus x squared. So it's going to be plus or minus root 3 minus y, I think. Right, let's see. You're going to get x squared minus 3 negative, yeah, okay. So these are functions of y that are going to be in our integral bounds. All right, so if you split them at this line is actually y equals 1.5. Okay, and how we find that is that, well, we remember previously when we did the other order, we have root 3 over 2 as x equals root 3 over 2 as their intersection points. Okay, so we're going to take this guy, plug him into either one of the functions, and we're going to get, so this one's the easier one. So if you plug them into that function, you're going to get y equals 1.5. Okay, so that's that line right there. So now we're going to start writing our two double integrals. So in this one, we're going to go from 0 to 1.5. So from here to there. And then we'll get back to this integral later. And we're still in dx dy. And then we're adding it to our second double integral, which is going to go from 1.5 to 3. And you're integrating, we'll do that in a second. And it's dx dy again. Okay. So what we can notice now is, so we're gonna do our favorite. Oh yeah, so if we're summing up the area from 0 to 1.5, we're gonna have this area underneath that line, right? And then the second one, we're gonna have this one after. And then when we get those areas, we're gonna add them up, and it should get what we had earlier. But we're not gonna evaluate the whole thing. It's gonna take a while. But they should be equal. Okay, so let's do this for this one. Okay, from 0 to 1.5, where is our favorite line that's going in the positive x direction gonna hit? Okay, so we pick this guy again. He's going, boop, he hit his first curve. He's going through the region we're gonna be integrating, hits the second one, and he's out. All right, the first curve he hit, yes, that's x squared, but we need a function of y in our bounds. So is it plus or minus root y? Okay, it's negative root y, right? This one is negative root y. Okay, and then he's going in the region, and then he comes out at positive root y. Okay, so those are our bounds for the first one. Now the second one, You pick another line, but this guy's above 1.5 to 3. Or he's above 1.5. He's between y equals 1.5 and y equals 3. So we're going to choose this guy. So he's going. He hits the first curve. He's in the region we're going to integrate. He hits the second, and he's out. All right. So similar situation here. Is it plus or minus root 3 minus y? That is the first one. Well, it should be minus root 3 minus y. Right? Minus root 3 minus y. Not the positive, because for y values, like, I don't know, one y value that's in here is like 2. If we plug in y equals 2 into the negative, we're going to get 3 minus 2. That's root 1. And that means x equals -1. And we're in the negative x region, so that lines up. That means the second part that comes out is going to be 3 minus y, positive 3 minus y. Okay? And so evaluating both of these integrals is going to give us what we got in the dy dx order, which was just, so this guy is equal to the integral from negative, what is it, root 3 over 2 to positive root 3 over 2. That spanned from negative x squared, or positive x squared, to negative x squared plus 3 dy dx. Okay? So, if you get an integral like this on a test, you probably did something wrong. You should probably switch orders, because I've never had to deal with any of these outside of my homeworks. But it's good to know how to do them. Okay. Now we have one more example before we move on to test problems. And this is something they really like to do on tests. You know, maybe we'll just do the test problem version instead, because it's actually really similar. Okay. Yeah, let's just move on to test problems. We'll do this one, which is similar to the example I wanted to show. So it wants you to evaluate this guy. 0 to 1, root y to 1, y e to the x to the 5th dx dy. All right, bro. So you look at this, you're like, man, e to the x squared isn't even integrable by traditional means. Well, there's no elementary antiderivative. Anyhow, so how are you going to integrate this? Well, what you have to do is reverse the order of integration. So you have to turn this guy from dx dy to dy dx. Otherwise, this is impossible. Okay? So to change him to dy dx, we have to observe the region that's here. Now, there was a little... especially for double integrals where you have to switch your order of integration, there was a little thing I liked to do where you look at, so this is, I don't know, this is, I'm weird, but this looks like a square to me. You have, and at every corner, you have a bound. Okay? What you can do to reverse this and turn it into dy dx is there's a way that you could always rearrange them in the same way every single time, and it's never failed me. What you're going to do is you're going to look at this bottom left bound, 0. You're going to copy him over, and you're going to duplicate him in the bound across from him. All right. You take this bound, and you move him up to here, but you change him to be a function of the other variable. So this is, right now, this guy is x equals root y. So that means y equals x squared. So you put x squared up here. Okay? And then you're going to take this guy, and he's getting scared. Okay? He's getting scared because this guy's jumping onto him. So what he's going to do is he's going to run away, and he's going to go right here. And this guy's still 1. Okay? This has never failed me. My friend said it failed him once. I don't believe him because it's never failed me. You can fact check this with any problem you do. It's always worked for me. And we'll do that in a moment. but it's always worked for me. I'm not sure. Maybe it's just a pattern. I don't know why the pattern is true, but I've always noticed this, and it's never failed me. All right, so that's our integral. If we want to confirm these bounds, what we could do is what helps me is just drawing out what's happening. So y is ranging from 0 to 1. So from 0 until, I don't know, say 1 is up here. Y equals 1, y equals 0. Okay. And then x is 1 right here. So this is x equals 1. And he's starting at root y, which is the positive end of y equals x squared. So it's it's something like that. Okay. And you want the region that's bounded. So, I mean, he has a top side and a bottom side. The only part that's bounded is this right here. That's this guy right here is R. Okay. Okay, so now if you want to switch the order, you want to change it to dy dx, right? So x is going to go from, what is it? It's going to start at this point right here, which is 0, and it's going to go till x equals 1. And then your y, pick your favorite y line. It's going this way. He's jumping. Oh, he's starting at y equals 0. And he's stretching through. He hits this guy, and that guy is y equals x squared, because we have to change the function that it is. Yeah, if you don't change the function that it is, then you're going to integrate this function of y, and you're going to get a function of y in your dx integral. And it's just like, bro, what's going on? So yeah, make sure you switch it. And you see we got the same result for our bounds. Okay, so now let's integrate him. He's dy dx. And you could pull this guy out, right? Because you're in a dy dx integral. You're in the dy integral with a function of x. This guy right here, he's a function of x. So you could whip him out. 0 to 1, e to the x to the 5th. And now y dy. So you have integral 0 to x squared. This is your integral, your innermost integral. So this is half y squared. Oh, sorry, I'm really sorry. Half y squared from 0 to x squared. And that's going to give you half x to the 4th minus 0. Okay, so that's going to be that innermost integral. You could plop him in your dx integral now and pull out the half because we don't like constants. And now he's a u sub. So you do u equals x to the 5th du over 5x to the 4th equals dx. So you can pull out this 1 over 5, and you're going to get 1 over 10. You can change your bounds. Oh, it's still 0 to 1. Nice. And then you have e to the u du over x to the 4th, because we pulled out the 5. And you could cancel out this x to the 4th and this x to the 4th, and you're golden. Okay, so you got 1 over 10 times e to the u from 0 to 1, which is 1 over 10 times e minus 1. So that's option choice D. I haven't even saw this one before. Yeah, and it's right, free low. Okay. I really like double integrals in general regions, and oh my god. Okay, let's move on to the next one. Double integrals, this guy, plop. All right, so it wants you to find this one in the region R and integrate sine of x over x dA, where R is the region in the xy plane bounded by the x-axis, so that's just y equals 0. The line y equals x, so this guy, y equals x, and the line x equals 1, so this guy right here. So this is R right here and here. Integrate, okay, oh wow, they even tell you, integrate with respect to y first, and then with respect to x. So this is dy dx is what they want us to do. Okay, so we're going to draw our little blueprint here. We have sine x over x, and they told us to do dy dx. All right, so x, where is that stretching from? It's stretching from x equals 0 to 1, right? From this point right here till x equals 1, and that's when it stops. All right, what about y? Y is going from, oh, let's pick our line. He's going, boop. He hit the thing. That's y equals 0. All right, he's in our region of integration. He hits the top thing, and he's out. Okay, do we plug in, do we say y or x? Is that y or x? It's x. It's got to be x because you're integrating out of this y integral, this dy integral, you want to get a function of x. If we chose y, we would get a function of y in our dx integral, and that doesn't make sense. That's like the main point I want to get across here, because it happens very often, and it's a huge waste of time if that happens on a test. Okay, now what's really neat about this is this is a constant. We're in our dy integral. So if we integrate a constant, we just multiply it by a y times y from 0 to x dx. Still from 0 to 1 times sine x over x. And then this y is going to become x minus 0. So just x. And that's really cool because now we can cancel this out. All right. And now we just have a really easy integral. So this is negative cosine of x from 0 to 1. Negative cosine of 1, we don't know off the top of our heads. And then minus negative cosine of 0. Now cosine of 0 is 1. Negative cosine of 0 is negative 1. And then we have this other negative. So he's plus 1. So 1 minus cosine 1. So that should be option A. Boop. Boop. Yay! Okay. Really easy stuff. Okay, what's the next thing I chose? Oh, I already chose this guy. Let's do, I don't want to do a polar one. Okay, sure, let's do this one. I didn't even select this one for today, but hell, we'll do it. All right, so this one's telling us compute this guy, cosine of y squared, dy dx, over the triangle with vertices 0, 0, 0 root pi over 2, so 0 root pi over 2, so I don't know, that's that. And then root pi over 2, root pi over 2, so like that. So my guess is it's that. Okay. So so this is root pi over 2, comma, root pi over 2. This guy is 0, comma, root pi over 2. And then this is just the origin. All right. So a line that'll, so this line right here, that binds this is that's just the y-axis, so that's x equals 0. So that's x equals 0, right? Okay, so we want to also choose our bounds. So x is going to start at x equals 0, right there. So that's that bound. And he's going to end at this line. Okay, let's find that line. It's got a slope of root pi over 2. So it's got to be y equals root pi over 2 times x. Right? So when x is Oh, no, I think I made it silly. Okay. Yeah, that's its slope is 1. So that's just y equals x. I don't know what I'm doing. Okay, that slope is 1. So that's just the line y equals x. But remember, we need these to be constants, okay? Because we're on our outermost integral. So this is where we're at. And then this is just root pi over 2. Okay? I know it's tempting. I didn't even see that earlier, but now I noticed that we're on our outermost integral, so we only want constants. And that's the furthest it's going to go at x equals root pi over 2. So that's that. Okay, now y is going to go through this line. So if we're going through this guy, he's out. First, he's going to hit that thing we just talked about, y equals x. And this guy has to be a function of x. And then he's going to come out at, yeah, this is just y equals root pi over 2. Okay, sick. What's kind of bothering me, though, is I think we have to switch order of integration. And the reason is because you can't really integrate that. Okay, we could even use our tip right now and just play around with these bounds. So this 0, he's jumping here and he replaces this guy, so we have 0, 0. Then we take this guy, he wants to attack this guy, comes there, but we have to switch his function, so he's y. Then this guy gets scared and he jumps here, so this is root pi over 2. I mean, just like that, we quickly switched our bounds. Okay. So now he's a constant. That's sick. So you're going to go from 0 to root pi over 2. And it's going to be x times that guy. And our only x value here is going to be y. So you got y cosine y squared dy, right? If you integrate this, you could pull out the constant. You're going to get x from 0 to y, which is just y minus 0, which is just y. Then you multiply that by that, and you get that, okay? Okay, oh, sick. This is a u sub. So u equals y squared du over 2y equals dy. Sick. Okay. So now our bounds are going to be 0 to pi over 2. And we have y cosine of u times du over 2y. This cancels. You get half of the integral from 0 to pi over 2 of cosine u du. And that's just half times the integral of sine u from 0 to pi over 2. All right, so that's just half times sine of pi over 2, that's 1. Sine of 0 is 0, so it's half. Sick. So that's B. Yay! Okay. So yeah, that's what it is for today's video. This is honestly one of my favorite subjects. Everything that happens from this point on, from general regions on, is super fun. I'm really excited to keep teaching it. Okay. I'll see you guys tomorrow when we're gonna do double integrals, but yeah, in polar coordinates. All right. See you guys tomorrow.